2016 AP Physics 1 for response. Question number 3. A long track, inclined at an angle theta to the horizontal, has small speed bumps on it. The bumps are evenly spaced a distance d apart, as shown in the figure above. The track is actually much longer than shown, with over 100 bumps. A cart of mass m is released from rest at the top of the track. The student notices that after reaching the 40th bump, the cart's average speed between successive bumps no longer increases, reaching a maximum value v average. This means the time interval taken to move from one bump to the next bump becomes constant. Part A. Consider the cart's motion between bump 41 and bump 44. In the figure below, sketch a graph of the cart's velocity v as a function of time from the moment it reaches bump 41 until the moment it reaches bump 44. Over the same time interval, draw a dashed line at v equals v average. Label this line v average. Here's the diagram of the setup. Now, since our cart is going down these bumps, each bump would slow down the cart. And then as the cart keeps going down, it would speed up and then slow back down once it's the bump. Speed up, slow back down at the bump. Speed up and slow down at the bump. Let's start off with the bump. The bump means we slow down, so we will draw a sharp line going downwards as it's quite abrupt. Now as we go over the bump and we pick up more speed due to gravity acceleration, we would speed up. And we speed up over time, so we draw a linear sloping line like this. Now we hit another bump. That means we have another sharp decrease. After this bump, we keep going down the same distance. So we accelerate for the same amount of time, meaning we will hit the same top speed again. But then we hit another bump. So our speed drops back down. But then again, we have the same amount of time to accelerate. So we pick up back to the same maximum speed. And again, our top speeds are the same since we're given the same amount of time to accelerate. And the same amount of speed is lost due to each bump since the bumps are the same. That's why we have a very uniform diagram like this. Now our average speed would simply be the average speed of this entire duration, which would be aligned somewhat in the middle. So this line here is the average. Now for part B. Suppose the distance between the bumps is increased but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was with the bumps closer together? Briefly explain your reasoning. Well, let's think about it. Earlier we said that due to the distance between the bumps, that the distance meant that there is a certain amount of time for the cart to accelerate and pick up more speed. Logically, if we think that the distance is longer, then it'll take the cart more time to travel that longer distance. So with more time, that gives the cart more time to accelerate to a greater speed. So we can say this as greater than. With more distance between the bumps, there's more time for the cart to accelerate without being disturbed by the bump. So the cart will be able to accelerate to a greater maximum speed. That's why we check off greater than. Now for part C. The bumps return to the original spacing. The track is tilted to a greater ramp angle theta. Is the maximum speed of the cart greater than, less than, or the same as it was when the ramp angle was smaller? Briefly explain your reasoning. So this time, our angle is tilted to a steeper slope. So the distance between the bumps is still the same though. But with a greater angle, you can see that there's a greater component of force acting on it. As a steeper angle would mean that more of gravity is acting on it. So with this in mind, that means there's a greater gravity and a greater force. So the acceleration of the cart would be greater. So it would be greater than at the end. The greater angle, the component of gravity acting on the cart is greater. So there's a stronger force and thus acceleration, even though the time is less between the bumps. Through the kinematic equation, final velocity squared equals initial velocity squared plus 2a times the displacement. We see that the final velocity is only dependent on displacement and acceleration. The displacement between the two bumps is the same, which is delta x. But as said earlier, since the acceleration increases due to the stronger component of gravity, final velocity would thus be greater. That's why we can check off greater than as well. Now for part D, before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that is intuitively expected to be true. That way, the derivation can be checked later to see if it makes sense physically. The student comes up with the following equation for the cart's maximum average speed. V average is equal to C mg sine theta over d, where C is a positive constant. To test the equation, the student rolls the cart down the long track with speed bumps, many times in front of a motion detector. The student varies the mass m of the cart with each trial, but keeps everything else the same. The graph shown below is the student's plot of the data for V average as a function of m. So here's our equation again, and this is the graph. Are these data consistent with the student's equation? Briefly explain your reasoning. Let's look at this data. We can draw a line through the data points to visually represent the relationship between m and V average. So let's see if this makes physical sense. Well, we see that as m increases, V average increases. And this is due to our linear sloping line. So we see that yes, an increase in m over here, since it's in the numerator, that would also increase V average. So our linear positive relationship between m and V average is true. But another thing to note on graphs, aside from the slope, would be the Y-intercept. The Y-intercept means that if m is 0, what is V average? And this is the key for looking at graphs. You look at the slope first and then the Y-intercept. The Y-intercept here is 1, meaning a mass of 0 has an average velocity of 1. Now let's look at our equation. If m is 0, will V average be 1? No, we see that if m is 0, this whole equation is 0, meaning that through this equation, V average has to be 0 if m is 0. That's why this data is not consistent with our equation. No, through the equation, the y-intercept of the graph should be at the origin. But this graph shows a y-intercept of 1, contradicting the equation. Let's check off no. Another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. Does this equation make physical sense? Briefly explain your reasoning. So here's our equation for reference again. mg sine theta, this is the component of gravity. And earlier we said that a stronger component of gravity would thus mean a stronger acceleration and thus increase the velocity to a higher amount. And thus this would make our final average velocity higher. This part here holds true, our numerator holds true. And c is a constant, so we can just ignore it. Now our other variable is d. Well, earlier we said that if the distance between the points increases, that means the final velocity would be greater, and thus our average velocity would be higher as well. But since it's in the denominator of the equation, the opposite is true instead, where an increase in distance would decrease the average velocity. But we know this is wrong, as we said earlier. So no, through the equation, we see that an increase in distance would decrease the average velocity. But previously, we already noted that a greater distance between the bumps would allow the cart more time to accelerate, allowing it to have a higher max velocity and thus greater average velocity. Thus, the equation doesn't make physical sense, as the variable d should be linear related rather than inversely related. So we can check off no. So that would be it for the 2016 response question number 3.